Welcome, one and all, to the Cool Worlds podcast with me, David Kipping. This week we have a very special guest, and that is Adam Riess, who is perhaps, I think, the most decorated guest we've had on the podcast, and frankly, one of the most decorated scientists alive today, I think it's fair to say. So I had to write down all of the various prizes and awards he's been given. So check this out. First off, he is a Bloomberg Distinguished Professor and Thomas J. Barbar Professor of Physics and Astronomy at John Hopkins University. But he has also been elected as a member of the National Academy of Sciences, a very prestigious group. He has won the Sackler Prize in Physics, the Gruber Prize, the Shaw Prize in Astronomy. That's kind of like the Chinese Nobel Prize, which, by the way, comes with $1 million. That's a big deal. He's won the MacArthur Genius Prize. And here's the biggest one, the Nobel Prize in Physics in 2011. And that wasn't enough. He kept going. He got the Albert Einstein Medal. And then just in 2015, the Breakthrough Prize in Fundamental Physics. And he's really just trying to collect all the prizes he can. He must have a very impressive shelf somewhere in his living room. So very happy to have Adam join us. And, to have all those prizes, it's not undeserved. These prizes really come down to this major discovery that Adam was a part of in 1998, and that was that the expansion rate of the universe was found to be not just expanding, but actually accelerating in its expansion rate. So if you go back to the time of Edwin Hubble, this was, almost a century ago, he discovered that the universe was expanding. By looking at these distant galaxies, we could see that galaxies which are far away from us are moving ever faster away. So stuff which is nearby is moving slowly away from us, stuff which is far away, it's all moving away from us and all moving even faster and faster. So the interpretation of that is that the universe is expanding. Which is pretty strange. Like, space itself is expanding. But Adam Riess went a step further and found that not only is the universe expanding, fine, but the rate of expansion is accelerating. The universe is exploding. What a bizarre result. I think we would have expected that the universe should be fine. It's expanding because maybe the energy of the Big Bang has this recession speed that's still kicking everything apart. But over time, gravity should pull everything back down together. Should be an inward force, a compressive force. And yet the universe is doing the opposite. It's an explosive force. So this is very strange. We normally attribute this now to dark energy, but who knows what dark energy is? That's just two words that basically astronomers have made up, and we still don't really understand what that is. And it has been, one of the major tasks of modern physics to try to understand that. So an incredible discovery right there. But now Adam's got more interested in recent years in trying to understand why it is that different people, different telescopes, different methods find different answers for how fast the universe is expanding. Not everybody agrees. So if you use some techniques to get one number, if you use other techniques to get a different answer. So what's going on? This is called the Hubble tension, and it is a major crisis right now in astronomy. In fact, it's often called the crisis in cosmology. So I wanted to sit down with Adam and hear about this. And this is really kind of a follow-up to a previous conversation I had with Wendy Friedman on this podcast. So if you haven't listened to that before, either after this one, or maybe pause and go back to that one, but you really want to listen to that one because Wendy has a different view and an opposing view to some of the things we're going to talk about today. And it's going to sort of defend a little bit some of the numbers that her team is finding, and Adam's team are finding different numbers. And it's really interesting because either one of these methods is wrong, one of the teams is wrong, or maybe the universe itself is just a lot more complicated than we think. And there's something interesting going on, perhaps some new physics going on as to why we all are getting these different answers. So one of the most interesting topics, I think, in physics and astronomy and cosmology that's happening right now. I was very glad to sit down with Adam, so please enjoy my conversation where we're going to get into all of this, figure out what is going on. I just want to say that today's episode, this is video. If you're watching this on YouTube, this is on video. If you're watching this, if you listen to this on Spotify, iTunes, this is irrelevant to you, but if you are watching the video on this, just note that there is no video feed. We just have like a frozen picture. It's not that your video is misbehaving. Adam just didn't want this episode video recorded, so you'll have the audio, but there's just gonna be a still picture during the conversation, and at the back end, I'll pick up with you back on the video. Okay, thanks and enjoy. So the first thing I wanted to ask you about, Adam, was with the Nobel Prize yesterday being announced. And as a laureate, I'm sure you have feelings and reactions about the news. And it was kind of controversial on Twitter and social media. People are saying, hold on, how come machine learning is getting a Nobel Prize? What was your reaction to the news? I assume it wasn't a total surprise, but what was your reaction when you saw it?
I might have had a similar reaction. Not that machine learning isn't terribly important, terribly interesting, fundamental, but sometimes this is just a category problem. Like, oh, is that physics? And there actually is a lot of physics. I know a sort of, statistical mechanics and, how is it that neural networks operate? Do they find a kind of low energy state? Can we think of them in terms of entropy? So there's certainly physics in it, but, you also sort of think Alfred Nobel didn't know about computer science. And today, you would imagine perhaps different or additional categories, and in which case, it would be much more natural to put this in a, computer science Nobel Prize.
Yeah, I guess exoplanets was kind of controversial similarly when people were like, is that really a physics discovery? And I've often wondered if we discover life on an exoplanet, where would that go to?
Where do we give the Nobel Prize?
It's not really physics, right?
Physics. I think if that happens, we give it to both.
Probably
would be the only double Nobel Prize.
Yeah, that'd be fun.
Immediately.
Obviously, mostly, apart from all the gossip of happening over the last few weeks, there is a lot of news and excitement happening in the world of cosmology. And the Hubble tension is really what I want to talk to you today about, because it's something you've spent the last decade or so really digging into and trying to figure out what's going on. I want to ground everyone, though. So let's start kind of at basics so everyone knows what we're talking about. So this whole debacle revolves around the Hubble crisis, the Hubble tension. It revolves around this one number, h0, the rate of which the universe is expanding. And it's named after Edwin Hubble, of course, who maybe there's, people say, well, it should be Lemaitre as well thrown in there, but for good or bad, it's, that's the association we have. And if we go back to sort of, was it the 1920s, 1930s when he was doing this work, how were those early astronomers first measuring the expansion rate of the universe? What's the origins of this entire field?
Right. So they were trying to measure the distances to galaxies around us, and they were measuring the apparent recession speed, what you might think of as the Doppler shift, we call the red shift of the galaxies. And it seems counterintuitive, but it's actually harder to measure how far away galaxies are than the redshift. The redshift, you measure certain lines in the spectrum, and those lines get shifted. The wavelengths of light are stretched, it turns out, by the expansion of space. But measuring how far away things are is quite difficult because we don't have good intuition when we look at distant objects. We don't recognize things so easily. Like, when you're walking across the street, you see a car and you go, oh, look at that tiny little car. And then you say, oh, that's really a big car, but it's far away. And you do the mental math to figure it out.
Because you know the size of a car.
Correct.
So you can translate, but we don't, galaxies are different sizes.
Right. But you look at a galaxy and you're like, well, what is the real size of that thing? I have no idea. And you see lights in the galaxies. What are the real luminosities of those things? I mean, I'm not really sure. And, so that's the problem, is our lack of intuition. In the same way, or here on Earth, we also use our stereo vision, parallax, to figure out how far away things are. Maybe they're a few feet away, you can tell with your eyes. Or if you need to gauge something further out, you might measure from two different vantage points on the Earth to figure out the distance to the moon or something like that. Then when we want to measure the distance to the nearest stars, it turns out they're very, very far away. And so we have to wait till the Earth goes around the sun and measure from two different vantage points. And even then, it's very, very hard because that angle where the object appears to change is small. So distances have been the hardest. And so it's taken us centuries, decades, most recently, to get very precise measurements.
And how did Hubble do it? How was he getting
So
distances?
Hubble was measuring the brightnesses of some of the brightest stars. He was measuring the brightness of objects called Cepheid variables, which Henrietta Leavitt had discovered about 20 years earlier, this wonderful property. So Cepheid variables are sort of, made to order for us in many ways. Cepheid variables are some of the luminous stars we know of. They are supergiant stars. So they're massive stars. They're late in their stage of evolution. And so they are about as bright as, 100,000 to even up to 1,000,000 times as bright as our sun. And so we could see them very far away. And they do another wonderful thing, which is they pulsate. They kind of flex in and out. And the period with which they pulsate tells us about the mass or luminosity of the star. So when we see one far away, we can measure its pulsation period, and it tells us not just that it's a Cepheid variable, but the specific luminosity that it has, so we can measure its distance from its brightness.
So this is all using the local universe, of course, using distance measures of nearby galaxies, and not just nearby, but really as far as we can really apply this method. But I think a lot of the Hubble tension is in application to measurements from the CMB, so the cosmic microwave background. There is, I think the measurement is around 68 kilometers per second per megaparsec.
67 to 68, yeah.
Okay. Whereas a lot of the local measurements are giving a range of values, but often much higher than this.
Yeah.
And so
70 to 75 with a kind of average around 73 maybe.
Okay. And those numbers sound similar, but I guess the point is the error bars on these are very small. So this is what the Hubble tension is. It's like there's a 5 sigma discrepancy at this point.
Right. And so it's probably more than 5 sigma at this point. And the thing to make very clear is that we are measuring or inferring the Hubble constant in 2 completely different ways.
Yeah.
And so it's not guaranteed that they will agree. So when we measure the Hubble constant locally, first of all, I should say the Hubble constant is a measure of how fast the universe is expanding today, not in the past, not at some other time.
It's not a constant then, is it really?
No, it's not really a constant, but it's a number for sure that we ought to be able to agree on. And so when you want to measure something like that today, you measure things around you that are essentially telling us about the present universe. So we measure distances and redshifts, and following the definition of expansion rate, we measure it from the ratio of those 2 things. So it's the direct way, I would say, of measuring literally how fast the universe is expanding. The other direction, you start with the universe after the Big Bang, and the universe expands, and the light doesn't get out of the plasma for a long time, but eventually point called recombination occurs, and you have hydrogen atoms formed for the first time, and now the light can stream out, and this is the cosmic microwave background that we see. And there's a lot of information about the state of the universe encoded in the cosmic microwave background. One of the most important aspects of it for our story is that when we look at the heat map of the cosmic microwave background, we see a lot of fluctuations in it. And we can describe those fluctuations as different scales, different periodic scales spatially. It's called a power spectrum. And the primary or the strongest fluctuation we see, what we call the sound horizon. And that is the distance that a fluctuation in the plasma could traveling at the sound speed from the Big Bang till the moment that light can get out until recombination. And so when people look at maps of the cosmic microwave background, they see the angular size of that feature, and then they try to calculate what the physical size of that feature is using basic physics and an understanding of what was in the early universe, including the model of the early universe called lambda CDM. And once they calculate that, they then can predict how fast the universe should have expanded throughout its history, again, using this model, lambda CDM, which is, as we know, is dark matter and dark energy, neutrinos and atoms. But about 96% is dark matter, dark energy. And eventually they can make a prediction. It's really a prediction of how fast the universe ought to be expanding today. And so it's based on a lot of physics, and it's
very indirect.
But it's very indirect. It's very model dependent on lambda CDM. And as I said, lambda CDM shows up in 2 consequential places in this calculation. One at early times to model the size of this sound horizon. That becomes the standard measuring tool. And then a second time to see how the expansion history would propagate and change the expansion rate from essentially the constraint they get at the time of recombination at redshift of 1,000 to the present. And so if these 2 things don't match, the local direct measure of the Hubble constant and this predicted method, then it doesn't tell you exactly what goes wrong, but it could show up as potentially a consequence of new physics somewhere in lambda CDM along the way. And just to be clear, lambda CDM is a model of the universe. It is not, it's not Maxwell's equations. It's not Newton's laws. It's a phenomenological model. It's kind of a fitting function that describes the recipe of the universe based on what we have seen so far. But about 96% of the universe, dark matter and dark energy, are really phenomenological. I mean, we really don't know at a deep level, at a physics level, what those things are. I mean, we think dark matter is a particle, but we don't know whether it's collisionless. We don't know whether it's stable. We don't know if it has any other physics besides gravity. Dark energy, we really don't know. It may be a cosmological constant. It may be varying in time. It may be a field. It may be a breakdown in general relativity on large scale. So in order to make this prediction, we sort of have to trust that the most vanilla form of lambda CDM is right. So that's why it's a really powerful end-to-end test of lambda CDM. Some people think of this as a conflict if these two things don't agree. I mean, I see it more as an opportunity or a potential clue.
Yeah, it feels like lambda CDM, I think it was like the standard model, akin to like standard model in particle physics. It's not really fundamental in terms of its origins, right? It's more like scaffolding that we've put up in place to explain. No one predicted dark matter really. It was just sort of we started seeing evidence for it, and then we threw that in there.
It's an effective model. It's a working model, but I don't think many people think that in the future, as measurements get better and better, theory gets better, that it will stand up forever. That has generally never happened. And, you look at lambda CDM, and as I said, it doesn't have deep roots in physics at the sort of micro level.
So let's talk about the other methods. So we're getting 67 kilometers per second, 68 from the analysis from the Planck mission.
Right. 67.4 plus or minus 0.5.
There you go. You know the numbers much better than I do. And we're getting higher numbers or even a range of numbers from different techniques. So looking at the literature, I'm aware of 3 or 4 different methods of doing this local measurement. So Cepheids, we've already talked about. I guess which also connects to type 1a supernova, which we should mention as well.
Yeah, so maybe I should explain the concept of a distance ladder.
Yes. Yeah.
So ideally, we would measure distance and redshift and the ratio of the two would tell us the Hubble constant. In practice, because distance is hard to measure, we have to build a network or ladder of measuring tools. I mean, our favorite is parallax. It's simple. It's geometry. It's been known since the Greeks. But the problem is to get into deep space where the universe is expanding, the parallax angle, the change in the apparent location of a galaxy as you move around the sun would be infinitesimal. You would just never be able to detect that. So instead, we use parallax to calibrate the luminosity of stars in the Milky Way, because we can measure parallax, especially with the Gaia satellite now, throughout the Milky Way. And then we look for those same kinds of stars in more distant galaxies. Now, with those stars, even with the James Webb Space Telescope or Hubble, we still can't reach out far enough. So we calibrate those stars in galaxies that hosted type 1a supernovae is one of the best examples. So these are really great, what astronomers call standard candles. We think they blow up at very nearly the same luminosity every time. So it's a network. We call distance ladder. It's essentially 3 steps where one thing calibrates another thing, and you're using the fact that 2 of those things are in the same location, a distant galaxy, to know that they're at the same distance. So if you know the distance to one, you have calibrated the other one.
Yeah. So just to jump in there, because I think people might wonder, well, why not just use type 1a supernovae, right? Because if these are standard candles, then we know their intrinsic luminosity, then there shouldn't be a problem. But I think the truth is we actually, although we know that they should have a standard luminosity, we don't know what precisely that standard luminosity actually is. I mean, that's why we need the Cepheids and the parallaxes to figure that all out.
That's right. So type 1a supernovae are wonderful distance indicators, we call them, but they're relative distance indicators. Yeah. I could look at one and say, it's a quarter as bright as another one. I guess it's twice as far away. But that doesn't say how many megaparsecs away it is. You have to know the absolute luminosity of at least one of them before you can gauge actual distances.
So I guess a slightly precarious aspect to this then is that if one rung in that ladder has an issue, systematic or something, it's going to propagate up the chain.
That is certainly true. It's really most dangerous for the first rung in a way, because what you're asking of the first rung, let's say it's parallax, is for that to be correct, essentially. Then after that, the other tools, whether they be Cepheids or Type 1a supernovae or another star, you're only asking them to act differentially as kind of middlemen. That all you're asking is that the Copernican principle doesn't fail, that the fact that you have a certain kind of star or supernova in galaxies around us, when you see them in galaxies a little further away, that there's nothing systematically different between these two. And the Copernican principle says, yeah, that's okay, because there's nothing special about the place we live in the universe. And so in order for you truly to have a problem, a kind of a systematic error between, Cepheids or supernovae on rungs, would require some violation of that. And that would in many ways be weirder than almost anything else we're going to talk about.
Okay. So that's one method. There's also the tip of the red giant branch, or TRGB.
Right. So different things can serve the role of other things. So, basically the three rung distance ladder we're going to talk about, I would say in most generic form is geometry, stars, and Type 1a supernovae. Now, stars could be, in that role, could be Cepheid variables, but more recently people have used tip of the red giant branch. They've used other pulsating stars called Miras. They've used carbon AGB stars, so-called JAGB. These things are much newer, and they don't have the same history of use and tests, and they don't have as many geometric calibrations, but they are a nice way to kind of cross-check other aspects. Instead of supernovae, you can use other techniques. You can use surface brightness fluctuations. You could use the fundamental plane of galaxies. And in today's analyses, you basically see everything at various points substituted in to say, okay, is this thing or that thing having a big impact on the
So really, it's
result.
just that middle rung of the three steps in that ladder. It's the middle one that people are mostly switching and playing around with.
Well, they're also switching the third rung as well.
Okay.
The supernovae, they're switching for surface brightness fluctuations, fundamental plane, things like that. And even the first rung, we sometimes use parallax in the Milky Way, or we use detached eclipsing binaries, which are stars orbiting stars that give you a nice geometric system to determine distance. We do that in the Magellanic Clouds, or even as a third option, we use water masers in the galaxy NGC 4258, which is kind of a special golden galaxy because it has the perfect alignment of water masers in a supermassive black hole. And radio observations have succeeded in measuring the distance by Kepler's law to about 1.5%. So we use all of these to really cross-check different parts. But so tip of the red giant branch is just used as an alternative in the middle rung.
Are there any of these methods? It sounds. I think this is why it's a little bit difficult to penetrate this field from the outside, because there are so many techniques folks are coming up with to do this. But are there particular methods amongst this myriad of combinations that you think are particularly potent versus methods that you're more concerned about? Right.
They certainly vary in the precision that they provide and the reach that they have. Reach can be very important because it means basically if you're going to use a star to calibrate Type 1a supernovae, you have to be able to reach out far enough to collect a decent sized sample of Type 1a supernovae. But I think something that maybe this is a useful summary to people, in the most recent annual reviews article on this subject from this year, in which they do a kind of study and summary of all these methods. I think they list 17 different local measurements. They vary from 70 to 76, I think, but they're all higher than the Planck value. So there's no smoking gun of any, it's this method causing it or that method causing it. Just some have, I would say, higher precision. I have not seen any evidence that any one method is inconsistent with another method.
Okay, so with JWST, some of the news we've been seeing is there's basically two major teams now, right? There's many people working on this, but there's two major teams in the US that people are hearing a lot about. Your own team, Shoes, which maybe can you remind us what that stands for?
Supernovae to measure the Hubble constant for the equation of state of dark energy. So we initially thought that we were measuring the equation of state of dark energy, that we would measure the Hubble constant and it would help us learn about the equation of state of dark energy by combining that with the CMB.
Okay.
Right.
And then the other team is the Carnegie Chicago or Chicago Carnegie Hubble program.
There's that team. There's also there's another team that has received more JWST time than either of the other two teams, so they should be on your radar.
Okay.
They're the JWST TRGB surface brightness fluctuation team. Doesn't roll off your tongue, but they got a lot of cycle 2 and 3 time, and they've just started putting out results as well. That's Brent Tully at the University of Hawaii, and John Blakesley at NOAO, and Joe Jensen and Gaggendeep and others. So that's just in terms of JWST, that's another team as well. There's the Maser Cosmology project, which has measured masers into the Hubble flow. That's been they've had a fairly strong impact as well. So actually, I think there's quite a few teams. I recognize that people often, may see one or two more, or maybe the people involved in them are better known. But I think that this is a community sort of wide experience.
Yeah, lots of interest in it for sure.
Yeah.
And my first question on this is, JWST is obviously still kind of in its early days of what we hope is a long life, whereas the Hubble telescope spent many, many years, decades, in fact, doing this kind of science. Has JWST now caught up? I mean, even though it's a bigger aperture, just the fact that the amount of data is so much smaller, has its precision now equaling Hubble, or are we still not quite there?
No, it's still well behind. Now, Hubble had a 20-year head start, or more. And I would say at this point, the uncertainty in the Hubble constant coming from JWST is a factor of 2.5 times worse than Hubble's. But I don't think that's the right way to think of it. I think the way to think of it is JWST has certain capabilities that allow us to check the Hubble measurements for particular ideas that people had of something that could be a problem. So, for example, I've been measuring Cepheid variables for a long time with Hubble, and have measured them in the hosts of 42 type 1a supernovae. So that gives us the biggest set of supernovae and the most precise value of the Hubble constant. But the images from JWST are much sharper. They have higher resolution, and so they allow us to better separate the images of the Cepheids from other stars in the galaxies. This is a problem called crowding or blending. Now, we did not think this was affecting that it was not a systematic uncertainty in the Hubble measurements because we were correcting for crowding, but it was the biggest source of noise in the Hubble measurements because it's a statistical correction. And so when we got the JWST data, we were very interested to see what that would look like. And so we have now gotten about 2 years worth of data, and the measurements are much more precise with JWST, but the answer in the mean, it matches what we saw with Hubble for the same galaxies that we observed with Hubble. So when you compare, apples to apples, you get the same thing. So that, I would say, has increased our confidence in the Hubble data. Now, we can't use JWST all by itself to measure the Hubble constant well because we don't have enough data yet, enough statistics. So for Hubble, we have 4 geometric anchors and 42 supernovae calibrated. For JWST, each of the teams has 1 anchor instead of 4, and about 7 to 10 supernovae instead of 42. And so you won't have enough precision to resolve the tension because you've increased your error bars by a factor of 2.5.
Right. With the crowding, let me just ask you this simple question for you, but if we're using this this Cepheid law, which basically takes the pulsation rate and it turns that into a luminosity, and that's what gives our distance.
Correct.
So is the crowding that you're worried that because if it was blended, that wouldn't really affect the period, I would get at, right?
No.
Your period would be robust.
Right. The period doesn't change. What happens is, so it's still a standard candle in the sense that you have to measure the brightness of that Cepheid star.
Okay, right. And compare that to the prediction.
And compare that to the prediction. But the period standardizes or optimizes, what luminosity did you expect for that one? Was it a big Cepheid star or a small Cepheid star? But you still are measuring the brightness of the Cepheid, and that's the thing. The image of the Cepheid, its point spread function, is blended with the point spread functions of other stars in the field. And so the way we handle that problem with Hubble is we cannot deblend them because they can be so on top of each other. So what you do is you statistically correct for this. You throw fake stars into the images of known brightness, and then you measure them by the same process, and you measure the net effect of blending on the Cepheids, and you correct for it. So that removes the problem statistically, but it doesn't tell you maybe that particular Cepheid landed on nothing and another one landed on something else bright. And so you still have the noise of the process, you just don't have the bias of the process.
And are there other second order terms in this law that matter, such as metallicity of the Cepheid?
There is. There's a second order that of metallicity, and so that is something that we calibrate. But what is even better is in recent years, since Gaia came along, Gaia provides parallaxes of Cepheids in the Milky Way. Now, most of the galaxies where we observe supernovae are metal-rich galaxies, big spiral galaxies. And the Milky Way is also a big spiral galaxy. And so when we use and calibrate the distance ladder with Gaia, now we're really looking at Cepheids of the same metallicity. And so whether there is a metallicity dependence and how you correct for it makes very little difference, because you're now dealing with things that are what we call solar metallicity. So things that are very similar to the sun in metallicity.
So coming back to these different methods, Wendy Freeman was on the podcast last year, and she had a paper that was published in August 2024 with the CCHP team. And using JWST data, they report H naught of 68 using the J branch of the AGB stars. 70, I'm ignoring the errors here, but roughly 70 using the tip of the red giant branch, and then about 72 using the Cepheids. So that, I guess what caught everyone's attention about that result is that it seemed like the JAGB was right on top of the CMB derived result from Planck, or very close to. The tip of the red giant branch was kind of in the middle of the traditional Hubble tension, and then the Cepheids were in line with the Hubble tension.
Right.
So how do we make sense of this result? What should we take from this?
Yeah, that's a great question. So let's take the tip of the red giant branch and the Cepheid measurement first, because they measured that in the same galaxies. Okay, so one can actually compare those things. So in that case, believe it or not, the difference between 70 and 72 is not even one sigma, one size of the error bar. And the reason is because you need to measure both those tools, not just in the host galaxies of type 1a supernovae, but also in the reference, which in this case is the galaxy NGC 4258. And you only get one measurement for each of those. So the difference between those of 2 is sort of like plus or minus 3.
Okay.
And so those are not statistically different. They're not, that difference is not meaningful. And I get it when people look at numbers, they're like, oh, this number is higher than that number. Can I interpret that? And in the realm of experimental science, we also pay a great deal of attention to the uncertainties. And when two studies are not significantly different, then we can't conclude much. Those who are hearing about election polls every day are hearing things like, oh, this candidate is ahead of that candidate. Oh, but it's within the margin of error. And I think people now understand that means I can't conclude something. So that's the answer there. With the JAGB method, that group excluded a number of additional galaxies. And when we looked...
That JWST had observed?
That JWST had observed, but they, for whatever reason, found that they could not or would not be able to effectively apply this JAGB method to that. Now, in this case, what we can do is we can look at the Hubble Space Telescope, because Hubble observed all those exact same galaxies, okay? So when we look at the Hubble measurements, the subset of galaxies that they observed for JAGB would also give about 68 or 69, okay? So the point is, and this is kind of interesting and may surprise people, but what I'm saying is JAGB, TRGB, or Cepheids are not measuring the Hubble constant. They are measuring the distances to a set of galaxies. There are then supernovae in those galaxies, and those supernovae themselves have fluctuations. Some are brighter than others, even after we standardize them. So you could look at a map of essentially picture every galaxy and the specific value of the Hubble constant you expect from the supernova in that galaxy. Now, we've observed 42 of them, but if we picked the same 6 or 7 that they measured JHB with, we would also get 68 or 69. But that is a very limited data set because we have many more. We observed another sample with the exact same technique, JAGB, and we got 74 from that set. And the point is, what you should always be comparing is apples to apples. You shouldn't be comparing what Hubble constant do you get, but rather what value do you get compared to what Hubble got for the exact same objects. And in that case, the agreement is excellent. It's less than 1 sigma difference. So there is no significant difference yet detected between JWST and HST, no matter which method of measuring distances you use. They are all statistically consistent. It's just that you might subselect a particular small sample that gives a low Hubble constant or another one that gives a high Hubble constant. I'll give you a good example. About 5 or 6 years ago, after the Planck results came out, and they give H0 of 67, there was a ground-based CMB experiment from Chicago called SPT, South Pole Telescope. And they had measured a small patch of the sky, about 500 square degrees. And in that patch, they reported a Hubble constant of 72 plus or minus 2, something like that, okay? And I thought, oh my gosh, this solved the Hubble tension. This is the answer. Planck was wrong, I guess, right? And then people did analyses and found that Planck got the same answer on that patch of the sky. The problem is it's a small patch of the sky. And so this is a phenomenon we call either cosmic variance or small sample statistics, that you could take a small sample of a larger data set and you can get a different value, okay? And the question to ask is, do I get that same value when I use those same objects from the bigger survey or sample? And in the case of Planck, yes, they got the same answer. So that what that meant was just the opposite. It didn't solve the Hubble tension. It actually gave you confidence that Planck was right and that you would have to default to the full Planck data set. So what I would say about JWST is it has measured small samples of galaxies hosting supernovae, and the results it has gotten agree with what Hubble got for those same ones. And so, if anything, that should raise our confidence about the Hubble measurements, and there's no reason not to use the full sample of 42 supernovae and 4 anchors, which gives us the most precise measurements at this point.
Yeah, because it sounds then like there would essentially this sample was just almost unlucky. Like it was just it just happened to be
I did a Monte Carlo simulation of how unlucky the sample was, and it was about 2 sigma in the tail. Meaning, if you had randomly picked 7 galaxies out of the 42, you would have gotten a fluctuation down to 68 or 69 or something like that. A few percent of the time. So not crazy, not that it can't happen, but that is what happened. On the other hand, our group's sample from JWST fluctuated in the other direction. And a few weeks ago, we put out a paper showing if you just combine the 2 samples, now you have a bigger sample, which reduces fluctuations, and you get 72.8. And so the point is, you have to pay attention and not jump at the first small sample or the first small study you look at. These are much more limited studies compared to what Hubble has done.
But then can't you go back to the Hubble? I mean, for choosing the JWST targets, you could go back to the Hubble data, and there's obviously a range of different, for any method, there'd be a range of different H-naughts you get. And rather than picking the subset which happens to give you the smallest, you could try to pick a more representative group.
Yes, and so that's...
Why didn't JWST do that?
So the answer is sort of, people did whatever they did, but the point is, the way we solve this problem normally is we say, let's pick a distance-limited sample. So we say, I want every type 1a supernova up to a certain range of either distance or redshift. So what we did with Hubble was our final results were every type 1a supernova in the last 40 years out to a distance of 40 megaparsecs, which is the range that Hubble can observe. And that was 42 Type 1a supernovae or thereabouts up to the year 2021. And so that was all of them. But what the first JWST samples were not complete in that same way. They were selected by rules that I can't tell you exactly what they were. But when you merge the samples, the CCHP sample and our group sample, it is now a basically complete sample to 25 megaparsecs. And not surprisingly, you're seeing closer to a reversion of the mean because it's now...
That's the 72 number you got.
Yeah, 72.8. That's about 16 out of the original 42. So, it's harder to get a bad fluctuation when your sample gets bigger.
Yeah.
So it's basically sample selection differences. There's no finding of actual differences in the measurements. It's like if you took back to the election poll, you could take a very small poll and you could get a very surprising result. But we sort of know from statistics not to trust such small samples.
Right. Yeah, I think that makes perfect sense. And yeah, obviously there's going to be intrinsic differences between these galaxies that's going to affect this analysis. So you want that averaging power. That's where this really comes in.
Absolutely, absolutely. I could tell you about another new result.
Yes.
When we have a chance, that is really interesting. I think that bears on this and is totally out of left field in a way. This was a paper that we put out a few weeks ago, Dan Skolnick, myself, and others from the Desi team. So if you're familiar with Desi, Desi is a kind of all-sky, deep spectroscopic cosmological survey that is meant to measure the dark energy equation of state. And they released their first-year data already. And one thing that I think went under people's radar was a couple weeks ago, they put out a paper with one of the best measurements of the Hubble flow, of the Hubble diagram, essentially, which they measured from a method called the fundamental plane of early type galaxies. So it turns out that early type galaxies inhabit a very tight correlation between their surface brightness, their velocity dispersion, and their angular size.
Can you just define early type galaxies first?
Sure. So those are elliptical galaxies. And so they don't have complex structure. They actually have very simple, they're sort of virialized, gravitationally collapsed balls of mass. Not like spiral galaxies that have, fancy arms and interesting things going on. They're simpler systems. And so the fundamental plane is used to measure their distances. And so this was the most homogeneous, large sample of fundamental plane measurements in the Hubble flow.
How far away are these objects?
Yeah, so they're measuring them between a redshift of about 0.02 and 0.10.
Okay, so pretty nearby,
Yeah, but well in the range that we measure the Hubble flow. Same thing we do with Type 1a supernovae mostly. So they measured a very tight relationship between the value of the Hubble constant and the distance to the Coma cluster. Now, the reason it depends on the distance to the Coma cluster is they had to calibrate the fundamental plane somewhere, and they picked the Coma cluster because it's the richest cluster of early type galaxies. There are a couple hundred there. So the answer they got was essentially, you tell us the distance to the Coma cluster and we'll tell you the value of the Hubble constant. And what they actually express it as is they get 76 plus or minus 1.3, so small uncertainty, times 100 megaparsecs over the distance to the Coma cluster. Now, in other words, a canonical distance to the Coma cluster is about 100 megaparsecs. But if it's not 100 megaparsecs, then that would change the value of the Hubble constant they got. But as you hear, the value's at the high end again, 76. So we did a study of what's the best distance to the Coma cluster, and it turns out because Coma is such a well-studied cluster that people have been measuring its distance for many decades, long before the Hubble tension. So we looked at many ways that people have done this, and there's really a consensus of about 95 to 100 megaparsecs as the distance. Now, we found we could measure an even better distance by looking for Type 1a supernovae in the Coma cluster, and we found with these all-sky surveys that there's been about a dozen Type 1a supernovae just in the last 10 years in Coma. So we measured those, and we got an answer of 98 plus or minus 2 megaparsecs, so right in there. The point is, if you took the value that comes from the cosmic microwave background, H0 of 67.5, and you use that to calibrate Desi, you would predict the distance to the Coma cluster to be about 112 megaparsecs, which is further than anybody has found Coma to be in the last 30 years by about 60 studies that we analyzed. So what is clear is that this is a pretty pervasive problem. This is another way of saying the Hubble tension, but now you're seeing it with a completely different tool, not supernovae, but this fundamental plane from Desi. You're seeing it baked into a long history of measuring the distance to coma that precedes anybody knowing anything about the Hubble tension, and by a much wider range of techniques, from Telly-Fisher to the globular cluster luminosity function, planetary nebula luminosity function, surface brightness fluctuations, many ways that people have measured the distance to coma. So I think it's looking like, as Desi makes more of these measurements, they are going to connect more and more local structures in the universe whose distance we thought we knew by many ways. And I think we're going to keep seeing this issue that they're always further away than the cosmological expectation. So either we're misunderstanding something in lambda CDM, or all of our beliefs about and our knowledge of distances locally will be systematically off. And I mean, I don't understand what's going on or why,
either way.
But it's something interesting seems like is going on.
Are there any measurements? We've heard about Desi and these other techniques. Are there any measurements which agree with the canonical CMB value?
Other ways of inferring the value from the early universe, like for example, if you take a Big Bang nucleosynthesis, so you measure the deuterium abundance, the primordial deuterium abundance in galaxies that have had no processed material, and you compare that to what lambda CDM predicts ought to be the deuterium abundance based on BBN, that serves as a poor man's calibration of lambda CDM. And it predicts a value of the Hubble constant very similar to the CMB value. But that sort of just illustrates the dichotomy occurs when you make direct measurements, or you make this kind of model-dependent thing that depends on lambda CDM. Now, it's not trivial to say, how you would change lambda CDM in a way that would change the CMB and change Big Bang nucleosynthesis. Some people have looked at constraints that come even earlier than recombination, a period called matter radiation equality, and those also give the lower Hubble constant. So it's more or less a difference between local measurements, where we're measuring distance and redshift, and this early universe via lambda CDM route. There are other things that weigh in, like the age of the universe from oldest stars, but those tend to have other model dependencies, sort of astrophysical model dependencies. Lensing is becoming a player in this, strong lensing, and so I've seen a range of values of the Hubble constant coming from strong lensing systems.
And what is the future for, I guess we have a 5 sigma, and JWST is only really just digging into the data.
Yes.
What's the prospects if we move 5-10 years ahead? Where do you think we'll be, and how precise do we expect this tension to end up?
If we keep investing with JWST time, and I can't say that's up to the time allocation committee, it's a year by year. It's year by year. Yeah. But if we keep investing, there's no reason that the JWST data won't completely replace the Hubble data, and do it in a way where we will have higher precision than we ever had from Hubble. There are more opportunities to cross-check rungs along the way. And so I think that people are doing just the right thing. They're collecting more data, they're scrutinizing it, but the theoretical community is also trying to think of ways that you could alter lambda CDM and try to explain what we're seeing. So it's this is a very interdisciplinary problem in my view. A clue could show up in the cosmic microwave background, it could show up locally, it could show up on a theorist blackboard, or it could show up in some complicated data set. So there's a lot of ways to get a clue in this case.
So maybe it's always dangerous to maybe ask you to place a bet, but it sounds like if you were to guess whether this is a real physical difference, or merely a product of some error in the methods or the techniques we're using, I'm getting the impression you're leaning more towards the fact that this is real. What could you tell us? Is that true? How much confidence do you have that is going to be the outcome?
Right. I think something interesting is going on, and I don't consider an error in measurements interesting. I think that This has gone on a decade. It's received a lot of scrutiny. It's received a lot of resources in telescope time and people's time to look at. And while from time to time people said, oh, I think I see an error or whatever, there's nothing that is held up on the it's an error side. And so errors are something that in principle, there's a much clearer roadmap of how to check. We go, oh, okay, what's your hypothesis? Let me test that. Or, oh, we'll replace this component of the measurement with that. So we've done all that stuff. And so far, there's no smoking gun of a significant error there. On the theory side, to me, it's much more open-ended. It's like we could say that we don't know what causes it, or we don't have an idea that fits like a glove, but when do we run out of theory space? When do we run out of idea space? I mean, there's great parallels in the history of science you could find. Like, one of my all-time favorite is the precession of Mercury, if you know that story.
Yeah,
Mercury was seen to precess in the 1850s, I think, and people had tried to find a solution for that. And, they imagined that there was another planet, Vulcan, that was between Mercury and the sun, and they looked for it, and some people claimed to find it, and then other people said they didn't find it. And this went on for about 60, 70 years, people doubting the quality of the measurements of Mercury, things like that. And then, of course, along comes Einstein with general relativity, who reinvents the way we think of gravity. And one of the very first things Einstein did was calculate the orbit of Mercury and realized first that in his theory of gravity, Mercury will precess, that Mercury is so close to the sun that it lives in a stronger gravity regime than Newtonian physics is used to or deals with. And so
new physics, yeah.
That's right. So that in the case was new physics. But the point is, right, if in the 1860s or 70s, you and I had done the very best search for Vulcan, and we had absolutely ruled out the possibility that there was a Vulcan, and we did the very best measurements of the precession of Mercury, and we were utterly convinced that those measurements were right. Could we have concluded or discovered general relativity by the precession of Mercury? No way, right? And so the theory space is a little more unlimited, and it's harder to say we went through all the ideas and there are none, because it's that space is much harder to confine. But we do know, and I think it's fair to say, that there are a lot of unknowns in the cosmological model, and so there's definitely some room to play. It's just, is there enough room, and do we have the idea, and will it explain things? And I don't know.
So let's talk about that. What kind of changes would we have to make to land a CDM to accommodate this? What are the, your favorite ideas which are emerging?
So the most straightforward way, at least on paper, is to shrink the sound horizon in the cosmic microwave background. And the way you do that, so this is essentially the size or scale of the largest fluctuation that you see. And the way you do that is you cause the universe to go into recombination earlier than you thought. And the way you do that is you make it either you inject more energy in the early universe, you make it expand faster at early times so it thins out and goes into recombination earlier, or you can make it more disordered at early times, more inhomogeneous. And so people have tried things like that, inhomogeneous from, primordial magnetic fields, make it inject more energy with episodes of dark energy, what's called early dark energy at early times, or some kind of relativistic particle at early times, another neutrino.
Doesn't this go again? I mean, the CMB is so homogeneous.
We assume it is completely homogeneous, or as homogeneous as it starts with quantum fluctuations and a certain power spectrum,
right.
But not much more than that, or if not inhomogeneous, that it organizes faster than gravitational instability and baryon pressure and those things would do. Basically, some kind of physics that is not exactly what we think. If the electron mass changes during that time, if there are changes in physics itself at the earliest times, that would be something that could do this. I mean, we have a certain description of physics and of the composition of the universe, and we follow that. But if there is a big surprise there, if dark matter has interactions, when the universe is extremely dense, if dark matter can interact, and if that has consequences for the calculation of the cosmic microwave background. So or another possibility is late time. So instead of changing before recombination, you change the expansion history later so that you do it with dark energy. So, initial results on dark energy were indicating that our dark energy looks a lot like a cosmological constant, in which case we have this tension. But if instead it's kind of a field that changes the equation of state of dark energy, then sort of all bets are off for that. And actually, speaking of Desi results, several months ago, Desi put out some results that combining everything, dark energy looks like it might not be a cosmological constant. It might, at 3 sigma, be like a thawing dark energy. Now, if dark energy is not a cosmological constant, I would say sort of all bets are off in terms of when we talk about the Hubble tension, we talk about connecting the beginning to an end with a certain model. If that model is not right, I need to know what to replace that model with before I'm willing to go back to making that connection. So I would say there are several uncertain things, a number of tensions in the air, and good data, and we're sort of like scientists, we're sleuthing through the case.
It's exciting. Is there a prospect of with new CMB data? So obviously
Yes.
Planck's kind of the state of the art,
Right.
but there's like the Simons Observatory.
Right, and there's ACT and there's SPT data. Yeah, I mean, they could certainly see signals of new pre-recombination physics. Basically, if they see any wiggles in the power spectrum in modes that they haven't checked yet that don't fit lambda CDM, that could be a signature of new physics. It might relate to the Hubble tension, it might not too. But that's why it's such an interdisciplinary problem, because when we see the Hubble tension, it tells us that something doesn't fit, but it doesn't tell us what that is. And so you can look for it, showing up in different times in the history of the universe.
So what are you most excited about with maybe with cycle 4 or the next year or two?
Right.
What are you?
Well, I'm certainly very excited to see more JWST data. This third group, the TRGB SBF group, expects to have a major result out in the next month or so. I want to see what that result looks like.
That's totally independent of you, right?
Totally independent of us. Yeah, nobody from the CCHP or SHUS is in the primary collaboration of that, and so I'm interested to see. And they're using tip of the red giant branch and surface brightness fluctuations. So nothing that they don't use Cepheids like I primarily use, or type 1a supernovae, and so that seems relatively independent. The TD Cosmo lensing team says they are going to have a milestone paper with significant new developments on this problem in the next several months, and I'm looking forward to see that as well.
Busy few months. Then.
Yeah. So I'm looking forward to that. I think the ACT team will have new CMB data, so there'll be new, shoes dropping, no pun intended. And I think we'll keep sort of following this as best we can.
Great. This is a very exciting time then. Thank you, Adam, for joining me on the podcast and telling everybody about all your work and what's going on. I'm sure people are going to be asking many questions about this, and hopefully we can update them in the future, because this is a topic that so many people are excited about right now.
Sure. Yeah. Great to be here. Thank you.
Yeah, thank you. So that was my conversation with Adam Riess. I hope you enjoyed it. Thanks for tuning in. One thing I want to sort of close by thinking about this conversation is just how active and how many questions there are in the field of cosmology right now. Listen, when I was an undergraduate student, I was fascinated by cosmology. It's one of my favorite classes, and exoplanets too, stellar astronomy too. But cosmology had a special fascination. This is trying to understand the universe itself. That's very profound. However, when talking to professors at Cambridge, this was at the time, I felt a little bit put off by the idea of studying cosmology. There was a sense from interactions I had with different faculty members at the time that really cosmology was in a very mature endgame phase, that all of the real breakthroughs, such as the work of Adam, discovering the expansion rate of the universe, the accelerating expansion rate of the universe, that work had been done. And now it was mostly a case of just measuring the various constants of reality and cosmology down to ever greater precision. Precision cosmology. That would be what we'd be doing. We'd just be getting it down to 1%, 0.1% precision, and wouldn't really be any fundamental insights to that. We're just doing it for the sake of knowing these numbers. And so that depressed me a little bit as a student. And I think it's totally wrong. I think it was totally wrong then to have said that. Maybe it was just a miscommunication of professors at the time, but yeah, I definitely don't think that was true then, and it's certainly not true now, as I think is hopefully very clear from the conversation I had today with Adam, but also the previous conversation with Wendy Freeman that I recommend you check out for some context about this conversation too. So listen, if you're someone who is studying out there astronomy, physics, and you have that same wonder as to when is a good time to get into these fields, there is always a sense that the field is done. It's easy to make that interpretation. Oh, all of science is figured out. And it's almost always wrong. And we're actually incredibly naive and arrogant to think that we have completed the story, and we are barely scratching the surface of what is truly out there. And Adam's discovery of the expansion rate of the universe clearly, broke a lot of expectations about what we might find. And the Hubble tension, I think Adam lays down a very convincing case as to why this could be real. There really could be a fundamental difference between the expansion rate of the universe that you measure using the early universe, using the Planck telescope, the study of the cosmic microwave background, the earliest epochs of the universe, and then extrapolate that rate forward. That rate seems to disagree with the rate we actually see using Cepheids and type 1a supernova around us. That disagreement is really profound because it means something, if it's true, is wrong with our fundamental theory of how the universe works. And that is exciting. For astronomers, for cosmologists, for physicists, that is the most exciting thing that can happen when there is something new. And the story is not complete. There is new things to be discovered. And so if you are a student, I would say, look, this is as fascinating and interesting a time to get involved in this subject as any other time. And if you're just a layperson and astronomer, like most of us are, then I suggest, listen, this is a story that you really want to tune into, because in the next few months, next few years, I think we're going to see some really important results coming out that are going to change the way we think about the nature of the universe potentially. So, of course, I'm going to be covering that on the Cool Worlds main channel, and of course, trying to interact with the cosmologists here in the Cool Worlds podcast to give you the latest insights from the folks who are actually doing the work. I think that is a really important point, to actually speak to the people doing this, and hopefully you are enjoying those conversations. If you are, if you think what we're doing is important and worthwhile, there's a way to support it, right? There is a way to support it. And that's to head to coolworldslab.com/support. That's coolworldslab.com/support. When you head there, you can actually become a donor, not really directly to the Cool Worlds podcast, not directly to the Cool Worlds channel, but simply to my research team, the Cool Worlds Lab. Now, we, of course, don't study cosmology, but we are studying exoplanets and life in the universe, which I think are equally very profound questions. Are we alone, and who else is out there? So if you think that is also worth supporting, go check that out. And of course, really by supporting our research, you support this work here on the podcast directly and indirectly too, because the more support we have, the less time I have to do writing proposals, grant extensions, things like this, and the more time I can spend making these podcasts and talking to you on the Cool Worlds YouTube channel. So if you think this is important, hopefully it's a nice way that your money is actually going to real research. Not very often you get to be able to do that. Head to the coolworldslab.com/support to be able to do so. So thanks again, and I'll see you in the next episode. Stay thoughtful and stay curious.